Very good. So yeah, thank you very much, Federico. Thank you for the invitation. It's quite exciting for me. It's the first time I'm at such a summit, and I wanted to split the talk into two parts. I couldn't help to tell you a little bit about the science we're doing. Very really a glimpse only, very superficially, but maybe I have to go a bit quickly on this part. And then the later part is the organizational part, which is I think you want to hear from me much more. There's one big difference between our science and large language models, AI. There is basically no private competitor in our field. While in your field, of course, there is. Okay, so it's really all made of a handful of particles and forces. This is how we usually start, and you've probably seen this before. We start with a fly, which is made out of molecules, and then the molecules are atoms with a nucleus, atomic nucleus in the center, and electron clouds around it. This nucleus is made out of protons and neutrons. And the neutrons and protons are not elementary particles. They're made out of quarks. And for the moment, the universe in this way is a very strange place. We think these electrons and quarks are elementary particles, but probably if we had enough energy to resolve it, it would actually not be elementary. And then without some remarkable mechanism at play, elementary particles would have no mass. So a big question is how these elementary particles get mass. And in reality, it is more complex than this, like always. We have, this is what is called the standard model of particle physics. So the particles I showed you before is the electrons and these quarks here, but in reality, we have 3 generations of matter particles. They're getting heavier and heavier. And if we create them, they instantaneously decay into the light particles. So these are all matter particles. And then we have force carriers, which carry the electromagnetic force, the strong force, and the weak force. The weak force is radioactivity. And then we have this very, very strange, completely new type of a non-universal interaction, which has nothing to do with the other forces. It's a very simple particle, actually, but the underlying principle is very, very deep. And so how do we know all this? All these particles with this little explosion here were discovered at accelerators. So you see that the main tool to study particle physics is accelerators. And so that's why I'm coming back to this. In reality, this all is, in fact, a mathematical framework. Particles are excitation of quantum fields, which are all around us in space and time. And so it fits on a mug which you can buy at CERN. There's also t-shirts of this version. And it's incredibly predictive. So I wanted to give you one hint of the predictivity of this model. The magnetic moment of an electron is actually a very complex property, and we can predict it to these amount of numbers here, 10 to minus 10, and it is in agreement with experiments, a very precise measurement. So it is a very precise theory. Now, we want the standard model not only to describe the world today around us, but also the entire history of the universe, starting with the Big Bang, 13.8 billion years ago, which is here at the beginning here. And this is the size of the universe, and this is the time axis. And after the Big Bang, the universe was expanding very fast. And in fact, the energy density was reducing. We have very high energy density at the moment of the Big Bang. And in these accelerators where we collide protons at very high energy, we place ourselves here at the LHC at 10 to minus 12 seconds after the Big Bang. And this is the very moment where particles, elementary particles, received mass. Before this, particles were massless. After this, particles had mass through what we call the Higgs mechanism. And the physics was, in fact, very different at the beginning. There's still a number of questions related with this. For example, it seems like at the beginning, we believed there was as much antimatter as matter. All the antimatter had disappeared, and we've only left with matter today. We don't know why this is. Then from gravitational observation in space, there's a huge amount of dark matter. In fact, 5 times more dark matter than visible matter stars and clouds. And we do not have any idea what this dark matter is about. Then how do elementary particles obtain mass? This mechanism is something we want to study in detail. And then there is a big philosophical question. In fact, we do not know why the laws and parameters of physics are set in a way to permit complex chemistry and life. In fact, if you take all the parameters of the standard model and you play God, you dial them around, you will almost always end up with a completely doomed universe where you can never, no stable atoms, nothing. So it seems like there's a huge fine-tuning which creates the parameters of the standard model exactly in the way to allow complex chemistry, biology, and life. And this is a very, very deep question where we have no idea why this was like this. There are a few ideas, but we have no real clue. Okay, so exploring the physics near the Big Bang requires a huge accelerator because we want to achieve these very high energies. And this was realized by the Large Hadron Collider, which is a 27-kilometer accelerator and collider, 100-meter around. So in the Geneva area, close to the Jura, I've shown it, going to show a picture. So then we accelerate the protons in this accelerator more and more through, we give it a kick whenever they turn around, 11,000 times per second they go around. And we can, through radio frequency field, we can give them all the time more and more kicks. But at one moment, they will be so fast that the magnets which keep the protons in the trajectory will not be strong enough and the protons will not stay on orbit. So the strength of the magnetic field is determining the energy we can achieve. So that's why a lot of CERN research goes into high field magnets. And then we accelerate protons and ions to multi-tera electron volt scale energies before they get into collisions. And in addition, we not only need to accelerate the particles, we also need to see what comes out of the collisions. And there at the collision points where the two beams cross, we build gigantic particle detectors like this part, which is Atlas. This was in 2006 while it was still being put together. So there's an inner part of this which is still to be filled here at this moment. So making this possible rests on sustained and focused international collaboration. There's no way to do this as a laboratory on its own. And it also means embracing collective authorship on publications. So this is often something which people are horrified about, but it is really a strength. So this is the observation paper of the Higgs boson in 2012. It had 2,932 authors in we have now 1,500 papers, all peer-reviewed, and all of them have 2,900 authors, and 250 institutes are also on this paper. So that's the price to pay. So then, as well as a strong international hub for large-scale experiments. So here, CERN is our center where we realize these worldwide experiments. So I wanted to give you a quick glimpse about the CERN, very short about the CERN history. So the objective was to create, so Europe was in ruins after Second World War, and the objective was to create a powerful and competitive infrastructure for fundamental research in nuclear and particle physics. Nuclear and particle physics at that time in the 50s, of course, was the big thing. And in fact, CERN got a lot of help from American physicists at the time. Oppenheimer and Isidore Rabi were playing a decisive role in the creation of CERN, who really wanted, because they had all learned in Europe quantum physics, and they wanted to restart physics in Europe. And so in 52, there was the Conseil Européen pour la Recherche Nucléaire. This is CERN, what CERN means. And then in 54, there was the foundation of the European Organization of Nuclear Research. And so this is a panoramic picture of the Merin site. It was just the countryside outside of Geneva. And then they started, this is the beginning of CERN, the first shovel here. And in 65, you see, this was the picture here. We had the first proton synchrotron, which at the time was already the strongest synchrotron in the world, but then taken over very quickly. There was a fierce competition between the US and CERN, and also in Russia. In the Soviet Union at the time, there were very strong accelerators. So then this is CERN today. You see an aerial picture. This all is the CERN campus. It's a small city, all this here as well. And there's a second campus here, over here. So for example, my office, the office of the LHC physicists are mostly in this building here. And this is another picture which I wanted to show you because it's a more modern picture. And you see here the new Science Gateway, which is a beautiful education and outreach center, which was inaugurated only one year and a half ago. And this was totally by donation money, in fact, from outside. And this is the Atlas experiment. These are the surface building of the Atlas experiment. The Atlas detector is 100 meters underground, and then the LHC goes around here and around here. So CERN, we put, in the constitution of CERN is science for peace. This is important. There's no military research. 25 member states, 10 associate member states who pay 10% of the member state fractions, and then 6 observer countries, and many, many, many cooperation agreements with basically all the countries who are doing research in this area in the world. And what is important is not the staff, but here the users. So about 12,000 people work with CERN experiments throughout the world. It's a very big hub, as you see. And usually when you go there, at 1 o'clock, for example, if you want to get in the various restaurants, food, it's very hard. It's a huge amount of people out there. So this is the aerial picture of the Large Hadron Collider. You see here the 27-kilometer ring. And there's the other accelerators, which are injectors, where the protons are pre-accelerated before they're injected into the Large Hadron Collider. And you see 4 interaction points where the 2 beams cross and produce collisions. This is ATLAS, ALICE, LHCb, and CMS. And I will discuss the ATLAS experiment, which is the largest of the 4 experiments. So the ATLAS experiment was designed, built, is operated, and now upgraded by a large international collaboration. Currently, we are 248 institutes from 41 countries, more than 100 nationalities, 2,900, as I told you, scientific authors, 1,200 PhD physicists are doing their research on ATLAS. And this is really a pride for us. This is a huge, I mean, it's fantastic to have so many young people around. It's really very nice to work with them. And they're not all at CERN, of course. They're in their institute and they come to CERN for meetings, for example. So then, very important also, 1,300 engineers and technicians. These detectors cannot be built by physicists like me. You know, no way. You need engineers who really know how to do things. And so this is very, very important. Overall, 6,000 members in the ATLAS collaboration. You see the world map there. So the detector is, I don't want to go into any detail. I just want to show you the size. So you see people here. So it's a very big detector. And the beams cross in the very center of the detector here. And then particles are created, heavy particles are created like the Higgs boson, and then it decays instantaneously into long-lived particles, which then penetrate the detector. And our job is to measure these particles to very good precision to deduce the particle which will actually decay in the center. So this is how it works. And it's like an onion. You have various different layers of high technology. And what is very important is that we need extremely low mass, radiation hard, because there's a lot of radiation in the center, and also fast electronics, fast detectors. And all these detectors are very special for this field. So we basically, everything of this is developed by ourselves. So this is a lot of development cycles go into this. Okay, so this, I wanted to show you one event for the Higgs boson. So you imagine the collision is here in the center, 2 protons collided, and then they produce a Higgs boson, which then decays into various particles. So these are muon particles, heavy electrons, and these are electrons. And what one does now is one measures the direction, momentum, energy of these particles very precisely and calculates the mass of the particle which decays. And then we do just a histogram, number of collisions versus mass. And then you see something like this. And you see a peak here of data. You see the data points in black. And this is the Higgs boson. So at a given mass, you have a resonance. You have many particles creating this mass. Okay, so now I wanted to nevertheless show you that we are also, of course, doing machine learning. In fact, neural networks have been used in particle physics since the 1990s. I've written myself a simple multi-layer perceptron with gradient descent. So this is very simple for your, and then since the 2020s, also boosted decision trees were very, very popular. But this is all kind of shallow learning at the time. So with respect to AI of today's. So now we are going also deeper here. We're using, in particular, graph neural networks with transformers, which are very performing to do reconstruction of particles, for example. Still, our models are much smaller than yours. We have maybe 1,000, maybe 100,000, maybe millions of weights to fit. You have billions. So it's a very much smaller models in our case. Okay, and then computing is very important. Computing was, in fact, organized since the beginning of the LHC as its own collaboration, the worldwide computing grid. This was the first time this was done. So we have about 170 data centers around the world, and now about 2 exabytes of LHC data stored throughout. Most of the data are, in fact, simulated data, because we have to compare our actual collisions with very detailed simulations to extract the physics. And we put more computing power into simulations than into the reconstruction of the actual collision data. Okay, so now the history of ATLAS and the LHC. It started in 1984 in Lausanne. There was a workshop. The tunnel was actually under construction already at that time, or just starting. And there was another accelerator, which was in the 1990s, with electrons and anti-electrons. And the idea was to use the same tunnel to build a large hadron collider, large proton collider. And this came up in 84, and then there were a number of workshops. I don't show everything. In 1990, there was a really constituent workshop where all the physicists came together in Aachen and really designed how the machine should look like, discussed the physics goals exactly of the machine and how the detectors could look like. And then one of these experiments, the ATLAS, wrote a letter of intent and also the other experiments in 1992. And this was the official birth of the Atlas collaboration. I was not there at the time. So then this followed by an Atlas technical proposal and then followed by a series of technical design reports, which you see here. And in 1997 was the formal approval of the Atlas construction. So we could start to actually spend money and construct. And then the start of operation, you see 10 years and in 2008. So now I go to this was the introduction. Now I go to the actual, what you really want to hear from me. So I want to go in a few slides, the pathway of large particle physics experiments, the governance and oversight, the collaboration organization, keys to success, challenges and pitfalls, and then a few maybe general lessons, which will be a little bit of a repetition of the previous points. Okay, so I organize this in the way that I have a summary here, and then I have detailed points, but I don't want to go necessarily through detailed points. I keep it here for you as a reference later. I think we should make these slides then maybe visible. And so in this case, I will just read through these points. So the large particle physics, so when we start, it's always bottom up. I think very similar to you here, it's bottom up. Colleagues get together and think about a new experiment, think about what is the physics case, what is the technology we need. And this evolves then from informal discussions through workshops, and then we do simulations. So we run simulations to understand what we can achieve in physics and what the technology we need. And then we start small R&D projects. So we build small detector pieces and put them into test beam, where we then analyze their performance. And then this creates then grows into a formal collaboration defined by a letter of intent, as you've seen before by Atlas, and a technical design report. And this is then approved by the government bodies and funding agencies, who are, of course, absolutely key in this endeavor. So following approval, memoranda of understanding are written, and they establish the responsibilities and deliverables of each funding agency. So the funding agencies, you really think of many, many countries, some countries have several funding agencies. For example, in Germany, you have 3 funding agencies. And so once these memoranda of understanding are signed, these are not legal documents. They are really basically expressions of commitment rather than legal documents. And so then this leads to the construction and the commissioning, and then we have to transit after we've built the detector into long-term experimental operations. So Atlas and LHC started in 2008, and we will be running until 2041. So it's a very long-term commitment, operation and the exploitation. And so this I've written in these points. I don't want to go through these points. This is just more detail on what I just said. So the next point is the resources review board. I wanted to go a little bit into detail. This you see here, this is a picture of the 1990s, and you see a particularity of our field. Only men at the time. You see not a single woman here, which is really terrible. And it has improved. It's not where we want it to be, but it has much improved, and we work on it. We really want to improve the diversity significantly. So the governance and oversight, large particle physics experiments combine exceptional technological complexity with international collaboration. This is a complicated thing to do. This requires robust management, review, and approval structures, and they have to be compatible between the countries, which is a challenge. At CERN, the projects are supported by a stable host laboratory framework. So what helps us a lot in all these things is that CERN sets the rules, and then the various funding agencies and countries actually adhere to these rules. This is very helpful. So not some country can start and say, I want it to be following my rules. It is CERN which defines the rules. And so if you can achieve this will be very helpful, I think. So then governed through coordinated national and international oversight. So there will be international oversight at CERN and through CERN, but then also in the different countries, there's national oversight of their deliverables to the project. So internal project management. So we have to have a project office inside, and independent technical reviews, and then a deliverable phase funding model. I will come to these points again. So the first points I will not repeat, but I wanted to clarify the internal project management. So the collaboration have a project office, which is important. This needs to be people who have experience on how to run big projects. And it's responsible for coordinating technical progress, schedules, costs, and risk mitigation across the various detector systems, and talking all the time to the institute. So this is an extremely important part of the organization. They usually report to the technical coordinator and then of course always to the spokesperson of the experiment. External technical reviews, so internal project management, then and external technical reviews, independent expert review committees who are not part of the project regularly assess the progress of the project milestones, and their findings are reported to the experiment, but also to CERN and to the funding agencies, to this resources review board I mentioned before. So that's very important. There's an external review, and if you're not doing a good job, they will tell CERN that you're not doing a good job. So you rather stick to schedule and cost. So then there's this resources review board, which is a CERN-led board of the funding agencies. So it has representative 1 or 2 per funding agency, and they are mandated to approve budgets or not. With financial legal responsibility, the RRB reviews the project status and approves, usually by consensus, this is very important, evolving budgets for construction, operation, and for experiment upgrades. So then the last part, which is very important, deliverable-based funding model. We are not interested in the money from the funding agencies. We want that they deliver detector parts. And so they commit to delivering detector parts. And if these detector parts were badly costed and get more expensive, they still have to deliver detector parts. This is on the paper. In reality, sometimes things become so much more expensive that other funding agencies have to help as well. So nevertheless, this deliverable principle is very important. You do not negotiate money with the funding agencies. You always negotiate deliverables. Okay, so finance is obviously the basis of everything. So the RRB provides the framework for resolving funding issues despite differing agency practices, and they're quite different. For example, in the US, there are contingency requirements. So if you say, I want 1 million, in fact, they think you need at least 1.5 million because they know it will be difficult. And would be useful in Europe as well, but of course, this makes from the start the project much more expensive. In Japan, there is a tendency not to quote the full cost and come after later. Conservative cost estimates are essential for building trust, while cost overruns are usually managed through the deliverables model, though, as I said, it's not always sufficient. So this is the picture of the costs of Atlas since 1995, where we started basically. So in 97, so we spent already a bit of money before approval, formal approval. Approval was in 97, until 2008, when Atlas was ready and started data taking. And you see here, this is in millions, so 550 million Swiss francs was the cost of 1995 Swiss francs of the work. And you see in blue, this was the memorandum of understanding numbers. And in yellow, you see cost to completion overcost. So 15% of overcost for a 20-year project, which is not bad at all, I think. So in the US type of costing, where they include this is only material costs, when they include all the salaries, it is actually 2 to 3 times more. This is important to keep in mind. And then since this, we spend about 21 million Swiss francs every year we get from the funding agencies for the operation of the detector, the experiments. This is the internal organization of the collaboration. We have a democratic structure with the policy making and executive branch. So it's like you have the parliament and the government. The parliament is the collaboration board, which is composed of each institute has 1 vote there, so about 200 votes. They set the policy and elect the leadership of the experiment. And then you have a management. They're all endorsed or elected by the collaboration board, who are the spokesperson, upgrade, technical, and resources coordinator. And then you have an executive board, which is, if you want, the government, which meets every week to discuss executive questions. And these are the leaders of the various subsystems of the experiment and activities. We have physics, for example, or online preparation. So these are all also elected or endorsed by the collaboration board. So it's deeply democratic how we work. So then keys to success. This is a picture of 2012, the announcement of the discovery of the Higgs boson at CERN, 4th of July. This is Fabiola Gianotti, who then was spokesperson of Atlas at the time, became then Director General of CERN, just finished her mandate now with the new Director General just starting. And what I wanted to say is maybe successful large collaborations are built on, this is very important, mutual trust, respect, and transparent and fair procedures. This is very important. With leadership grounded in excellence and expertise, not the resources they bring or because this is the most important country or most important group. This is very important. So open and inclusive governance through clear structures. You have you need a constitution, representative decision bodies, merit-based evaluation of ideas. When people bring new ideas, you should be open to it. Consensus building and collective ownership of major decisions. This is the collaboration board. If you take a major decision, it has to be taken by the collaboration board, not by a small group somewhere. So this ensures that all members, including early career researchers, have a voice and that innovation is encouraged and rewarded. In particular, for very long processes, you need to permanently innovate. If you stop, you're getting lame. It's very important. So the same points I bring here again, I maybe don't discuss those. So now I go a little bit more in detail into the challenges. This is one slide where I will not read the introduction, but rather the details. I wanted to go through these points because it's important. So staying on budget and schedule while focusing on mission critical developments is essential, and it's very challenging, in fact, as you know. So for example, from R&D to production, the first point, we're all physicists, we are curiosity driven. We love R&D. And then the transition to large scale production is very critical and often starts too late because we just want to continue to invent and not start to produce. It's very difficult, this part. Rising technological complexity. So modern technologies are increasingly complex and require very strong engineering support. And here we have a lot of competition from the market. They pay more for the engineers and technicians we need. And so they are costly and scarce in research environment. For example, we are developing radiation-hard, low power, high throughput ASICs, these small chips. And it is very hard, in fact, to do this in the research environment because it's so complicated these days. Technology down selection. So then, many groups have great ideas how to build an experiment. Then one moment you have to decide what do you actually use. And then this is a down selection. That's a very hard, a very difficult process because some have spent years of R&D and their work will not be used in the experiments. So here it's important that this is a difficult consensus-driven collaboration because we want to be our friends, but this is a hard moment. So it's important to have transparent criteria and decision processes so that everybody knows this is a fair process of down selection. So then the project management culture, industrial style project management may clash with the academic culture. Here I want to say it is essential to follow industrial style project management because you are talking to funding agencies who do follow industrial style project management. And so if you don't do this, you're not serious in their eyes. So it's very important to do this and to be a bit weaker on the academic culture. Strength of technical reviews. Expert reviews must be enabled to recommend stopping or restructuring projects when justification or feasibility is insufficient. This is a threshold which is too rarely enforced. We're very kind people. And when somebody develops something, you think that's the wrong way. We don't always tell them. But it's important to tell them to stop things when it's not going in the right direction. Pragmatism over perfection. The pursuit of technically perfect solutions can delay or jeopardize delivery. Pragmatic and robust technological choices often lead more reliably to the desired scientific outcome. This is also important in our field. Long-term funding commitments. Large projects require funding agencies to commit over their full duration. So remember, we started, the approval was in 97, we ran until 41. So this is a huge, more than 50 years of running. So we need funding agencies to support us for this full time. And this can be challenging, particularly for agencies in smaller countries or with limited experience in long-term big science investment. This is something where we have to always talk to the funding agencies and explain our particularity. So then managing ambition, over-ambitious project scopes increase risk and can lead to failure. Striking the right balance between the innovation and feasibility is very important. Okay, so this is my last slide on this. I think there's a lot of repetition here, but I'm quickly load through this. Collaboration out of necessity. So we don't collaborate necessarily because we're friends. We collaborate because this is the only way we can achieve these aims. And I think this is very similar to your field. Earn trust through delivery and openness. Very important. Everything you do has to be open science, as Federico was saying. Enable and don't control. Use clear governance and transparent decision, not a rigid hierarchies. Reward excellence wherever it appears. Leadership follows expertise and contribution, not seniority or resources. Plan the R&D to production transition early. Very important. Make this step when you think you're ready. Be pragmatic. As I said, robust, timely solution beat perfect ones that arrive too late. Make hard choices transparently. Down selection preserves trust when criteria are clear. invest in people, empower the early career contributors, and sustain the community. Anchor and stable institutions. Long-term success needs neutral, reliable hubs, as we have at CERN. And then remember the human side. Large collaborations is demanding. You have a lot of people all the time to talk to, lots of meetings, I can tell you. But it's deeply rewarding, nevertheless. And so I wanted to read you this. By joining forces with trust, openness, and pragmatism, communities like yours can achieve game-changing science and technology beyond the reach of any single group. And you will see, you will enjoy doing this. And I wanted to just say that also in our field, we are not at the end, we continue to evolve. There has been just a globally inclusive European strategy process for particle physics. And it was just in December, it has defined what should be the next flagship project for CERN. You probably have heard about this. We call this the Future Circular Collider. It's a huge project. So this is the Large Hadron Collider. And this is the Future Circular Collider, which goes under the Lake Geneva, behind the Salève, close to Annecy, 90 kilometers. It's a facility which should basically work throughout the entire 21st century, delivering lots of new physics. And it is quite a challenge. So thank you very much for your attention. And all the very best for your large-scale project in Colorado.
Well, I mean, for sure, there were a lot of points that were resonating with us. This was super fascinating. We have time for maybe one question.
So I'll stay all morning if you want to discuss later in the coffee break.
Thomas?
So, thank you for this overview. You made the point that Atlas started operation in 2008 and will continue until 2040. In terms of learning, I don't think anybody here would have even thought about what was going to happen before 2017. Most people have no idea what was going to happen until probably 2023. So you see and what's going to happen in 10 years, I would like to see anybody try to make a prediction.
Yeah.
So there are these different scales.
Yes,
and
it's a great
what I'm interested in or have seen is WLCG with our involvement in CHIP. And what I'm interested to hear in the Atlas experiment, how do you hold together the different cultures? And I mean now the Swiss culture of Atlas in the WLCG versus the American culture. The Swiss culture is probably the most difficult collaboration I've ever experienced in terms of adopting innovation. And the American on the other side with Brookhaven, Oak Ridge, they were always ahead of the game.
Yes.
Yet it's the same experiment. In the end, it's, you just ignore the Swiss there and you work with the Americans, or how do you hold these two parts together?
I think it's a mixture, because you always have to run the experiments. So while you're running
all the data analysis and all information technology,
all the data are coming in and you have to reconstruct them. So you need the WLCG working and operating.
Yeah.
This is the pragmatic side, maybe the Swiss approach. And then for the next stage, for example, we are currently upgrading the detector. In 2000, we're stopping in 26 for 4 years. And then in 2030, we restart. And then everything will be different. The detector will look completely different. And the computing will also be computed. So we're writing currently a TDR. And for example, there's a huge discussion coming from the US in using much more GPU resources, using even FPGA resources in the reconstruction. And so this is I think, a fruitful discussion. And then there are more conservative voices, indeed, more from Europe, saying we have a model which works extremely well, which serves us well based on, high performance CPUs. And we will see how this fits together. Well, at the end, we come to a compromise always. And the funding agencies also in the US at the end understand what we all want is this experiment to succeed and the best technology. And this is always important to keep behind. So if you have a great idea, but this can't work in the framework of the collaboration, then you accept it, because it's much more important that the experiment continues. And I think this everybody understands.
Okay. It's just that if you want speed, I think the two AI centers are the counterexample to the the Swiss Atlas information technology.
Okay.
And I think that's where we probably have to make a decision, how
I mean-
to keep the speed without losing direction, of course. That's the challenge.
So my personal view is I like a lot the innovation which comes from the US. It pushes us all the time. There's a lot of innovative power from there, and it's very useful for us. And so I wouldn't want to miss that. Yeah.
Let's thank Andreas one more time.